So one of the situations that you can have that basically using the entire parameterization is not necessary is this problem. We're trying to compute the flux of a vector field f of x and y and z equal to x and y and 0 on the surface of the disk, z equal to 2 and x squared plus y squared less than equal to 9. So this disk sits on plane z equal to 2 and includes the circle x squared plus y squared equal to 9 and anything inside that circle basically. So one thing is that a lot of times we just start by the parameterization and then we find basically we want to find the n and either plus minus that and find the f at g and then dot it with the n and compute. In this case, before even parameterization comes in, you can actually figure out what the flux is, and that's by looking at the vector field. Vector field is basically parallel to the surface of the disk. It goes like that. More in there, but they're all parallel. So there is no orthogonal components of the vector field going through the surface that is given here. Basically, how do I know? If I compute f dot little n to find orthogonal component of the vector field, what I get, and what is n? N is obviously orthogonal to z equal to 2, therefore it is n going upwards, so it's just k. And here, if I multiply x, y, and 0 dot 0, 0, 1, which is k, I'm going to get 0. And then the surface integral is going to be, the vector surface integral is going to be the scalar surface integral of f dot n of the orthogonal component, and that is this. And when this is 0, this is going to be 0. So this was a lot easier than parameters.